Thank you. Thank you very much for the invitation. It's always a great pleasure to be in South America and in Brazil. So thank you very much for this opportunity. So my talk today deals with the subject of nonlinear, dispersive, and wave equations. So, of course, it's a subject I've been interested for a long time. I'm going to talk about some kind of qualitative aspects of the theory, but I will concentrate on one particular equation, which is the energy-critical nonlinear wave equation, and I'll indicate later on where some of the results are valid in more general settings. So I start out with a nonlinear wave equation. And we consider the Cauchy problem. And let's say that 0 belongs to this interval. And H1 is the space of functions with gradient in L2. And L2 is L2. And so this problem is energy critical because when you rescale the solution in such a way that it still is a solution to the problem, the energy norm remains invariant under the scaling. And that's why the problem is energy critical. Besides being energy critical, the problem is focusing. And so what that means is that this linear differential operator and the nonlinearity have opposite signs, so they fight each other. And this leads to the possibility of singularity formation. Okay? Now, we consider solutions. I'm not going to define precisely what I mean by solution, but we consider always the class of functions which are continuous from the interval into H1 cross L2. And there is a well-developed local well-posedness theory, a local theory of the Cauchy problem. And this local theory says that if I have a very small data, then I have solutions that exist for all time, and they scatter so that eventually they behave as if they were a linear evolution. And then for large data, at least for a small time, you have a solution, and then some other things can happen. And we're mainly interested in what these other things are, okay, that can happen. Now, for a solution, there's a maximal interval of existence of a solution. I have a name for it. Yeah, so these equations are time reversible, so we go both forward and backwards in time. And this is the maximal interval, and what that means is that there's no way to continue the solution between this interval, beyond this interval, in a continuous way in H1. It does not mean necessarily that the norm has to explode. It could happen that as you approach, let's say, t plus, if t plus is finite, what's happening is that the gradient squared of the solution is concentrating like a Dirac mass, and therefore you cannot continue continuously. Okay. Now, for the purpose of this talk, we will consider bounded solutions. And so what this means is simply that if the solution ceases to exist, it does so because of concentration, not because of norm explosion. Okay. So we're considering bounded solutions. So first of all, you could ask me, are there any bounded solutions? So yes, otherwise I wouldn't consider them, but examples. First are scattering solutions. That means that there is u0 plus, u1 plus, such that u of t dt of u of t minus so I'll explain some notation. S of t will denote the solution operator for the associated linear problem where I just ignore the nonlinearity. And when I write S arrow of t, I mean the gradient of S of t and the ddt of u of t as a vector. Okay? And scattering means that this H1 cross L2 norm tends to 0 as t tends to plus infinity. Okay? And that's what I meant before by saying that eventually the evolution becomes linear. Okay. And this is an example of bounded solution. Now, it is interesting. Oh, I'm going to restrict my attention to dimensions 3, 4, and 5 today. And the only reason is that that's for higher dimensions, the nonlinearity becomes less regular. It becomes less than C2. And then there's some technical issues, but that's all. I mean, it's just for that technical point that I don't wish to address today. Okay? There are solutions. Which are bounded, but for which t plus is finite. So there are solutions that cease to exist at a finite time, but the norm remains bounded. And these were constructed for n equals 3 by Krieger, Schlag, and Totaro. For n equals 4 by Hilleret and Pierre Raphael. And for n equals 5 by Yannick Yindrich. I have to. So they exist in all the dimensions. Okay. And they're even radial in these constructions. There's another example. Of course, here we have an evolution equation, but we can ignore the evolution and consider static solutions. So solutions Q to the elliptic equation are also solutions to the nonlinear wave equation, and they're bounded because they don't depend on t. And it is well known, and this is a very well-known elliptic equation. It arose in the 80s in connection with the Yamabe problem in geometry. And it's a problem that has been studied extensively. And an example of the solutions is what we call the ground state. Let me write it for n equals to 3 so that I don't write lies. But it is a formula in all dimensions. Okay. Now this is the unique non-negative solution to this equation. It's also the unique radial solution. And when I say unique, of course, I mean up to scalings and sign. If W is a solution, minus W is also a solution. And these facts were used in the solution of the Yamabe problem. But there exist infinitely many variable sign solutions. Those were first constructed by Ding in the 90s, and there's a more recent, more explicit constructions due to Del Pino, Bacar, Musso, and Pistoia. Okay. Now this equation has some invariants of the motion that are very important in the study. The first one is the energy. Again, n equals 3, otherwise I don't remember the numbers. So this energy is a constant of the motion. It remains constant for solutions in the whole maximal interval of existence. Now, the fact that there's a negative thing here, a negative sign, tells you that you could start out with negative energy. Okay? And that's a reflection of the focusing character of the equation. And it's an early result by Levine in the early 70s that if you start out with data which has negative energy, you will cease to exist in finite time. Okay? And that's a construction argument, an obstruction argument, I'm sorry. And basically what Levine's argument says is that if you had a solution with negative energy that exists for all time, you could find a one variable function which is non-negative, and it's concave, and it lives for all time. And if you look at it in your heads, you can see that this cannot happen. Okay? Okay. So, for instance, W is a globally defined solution which does not scatter. It does not verify this property. And why is that? It's because if U scatters, then there's local energy decay. So if you look at the amount of energy in a little box, and the box doesn't move, and you go to infinity, the solution scatters, that has to tend to 0. But for W, since it doesn't move, it's a constant, so it will not go to 0. Okay? So in general, solutions of this elliptic equation are, as solutions of the nonlinear wave equation, do not scatter. Okay? Because of this. So what is my ultimate goal here? The ultimate goal is to understand completely the asymptotics of all bounded solutions. Okay, so this is the ultimate goal. And this is an instance of what is known more broadly as the Soliton resolution conjecture. Now, instead of explaining the Soliton resolution conjecture in generality, I'll do a little bit more of that in my talk on Thursday. I'll say what it says in this particular instance of this equation. So what that says is the following. U, a bounded solution. Well, let me call this, to abbreviate, let me say, that non-zero solutions of the elliptic equation, I will just say Q belongs to sigma. Okay? If you use a bounded solution, then the claim is that there is a number, J, solutions Qj to sigma, vectors Lj of length less than 1. If I take a sequence of times Tn, which increase to the final time, I can find scalings lambda j translation parameters let me do it again for n equals to 3. Otherwise I will die in the notation. But the same conjecture holds for all n. And a linear solution and we refer to this linear solution as the radiation term. Such that we have a complete description of the asymptotic behavior. So that I can write my arbitrary solution as a sum of traveling wave solutions plus a linear solution plus a term that goes to 0 in H1 cross L2. So it completely describes the possible asymptotics as superpositions of traveling waves and linear solutions. So you can think of this as some kind of Fourier decomposition at infinity for the solution, where you're giving a complete expansion. Okay? So what's the case of scattering? That's precisely when capital J is 0. So this is a complete description in the case when there's no scattering. Of course, I have to tell you what these guys are. What are the traveling waves? Okay. And this is a formula, but it's a well-known formula for people who work on the wave equation. It's mainly the Lorentz transformation in the direction of L of Q. So it's not exotic, but I'm going to write the formula once. And of course, I have to copy it because there's no hope of remembering it otherwise. And there's a more suggestive way of writing it. Which shows it explicitly as a traveling wave in the direction of L. And this happens for any vector which is length strictly less than 1, so that you're traveling at strictly less than the speed of light. Okay? So this is the big conjecture we're after in this particular example. So let me just say a few words about what is known about this conjecture. In 1912 and 13, with Ducaer and Merle, we proved this for the radial case. So this is proved in the radial case. And then there are no Lorentz transformations. They are not needed in the radial case. They destroy radiality, so you don't put them in. And these Q's are just plus and minus W, because those are the only radial solutions of the elliptic equation. Okay? Now, of course, there has to be some orthogonality properties between the lambda j's and the xj's that I haven't written, which are such that there's no interaction between the different waves. Okay. I could write them, but anyway. So the next case when this was proved is in the non-radial case. In dimensions 3 and 5, but for a perturbative regime. U near W, and this again is Ducaer, myself, and Merle from 2011. So, but what we want to now understand is a proof of this in the general non-radial case. Now, one of the things that immediately comes to mind is, what are these guys? Why are these guys here? Why don't you need more things? Why is this the complete list of objects that you need to write there? So, are these the only traveling wave solutions? So, the object of this talk is to address some parts of that issue. Okay? So, question. So you think that if this decomposition is going to be proved for a general function, then all the traveling waves have to be accounted for. Okay? Okay. Can people read if I write here? Yeah? Okay. So the title had something about compact solutions. So I'm going to now tell you what is a compact solution. Okay? A solution U has the compactness property, or is a compact solution, if there exist translations x of t, scalings lambda of t, such that when you look at the vector k, and now I have to write something long, So I'm modulating the solution by x of t and lambda of t. And here I have to put lambda of t to the 1/2. And here I have to put lambda of t to the 3/2, because that's the correct scaling. So this set has to have the property that its closure is compact as a subset of the space H1 cross L2. So instead of being a single function, let's say, it's a compact set. So it's something kind of close to being finite dimensional in some sense. Okay. So now this concept seems, at first sight, seems very strange. Why do you need such a concept, and what role does it play? I mean, certainly it was very strange for me when I first saw it. This concept of solutions, as far as I know, was first considered by Gangletas and Merle in the early 90s in an unpublished paper on the Zakharov system. It was then used extensively by Martel and Merle on their work on the KdV equation, and simultaneously also used by Tao in his works on asymptotics of solutions of the nonlinear Schrödinger equation. Okay? So why are these solutions important? I'll explain that in a minute, but now let me first give you some examples of. I thought that I eventually would need to erase. So let me erase here. So examples. Examples of solutions with this property are traveling waves. Right? If we go to here, this is x of t, and lambda of t is 1. Okay? So traveling waves are particular examples of compact solutions. The next thing, so the general question that we wish to address is, are all compact solutions Lorentz transforms of solutions to the elliptic equation? If we establish that, then all traveling waves are accounted for there. Okay? Okay. So for the linear equation, what are the compact solutions for the linear equation? This is very easy to answer. Only the zero solution. So the only compact solution of the linear equation is the zero solution. And this is an exercise in you can do it by Fourier analysis by taking Fourier transforms. It becomes very simple to prove this. Okay? It also, you can use this thing here to prove it for the linear solution. Because if you had a compact solution, all the tails would be very small as you go to plus infinity. But this tells you that the part inside also is very small for the linear equation. And therefore, you put the part inside and the part outside together, the whole thing would be very small. But by preservation of the energy, that's small for large time, but it's also small initially. And therefore, you only have zero. Okay? So why does one study solutions with the compactness property? And I guess I need to erase again. There's a very general fact. So this is another theorem with Ducaer and Merrill from 14, which says the following. Let U be a bounded solution of n algebra. So you start out with an arbitrary bounded solution, let's say non-zero. I mean, we don't want to study the zero solution. Suppose that U does not scatter. Because if it scatters, then we understand it's asymptotic. It's like a linear solution. So suppose it does not scatter. Then you can always find a sequence of times converging to the final time such that the solution along this sequence of times will converge weakly to a compact solution. So as you're approaching the final time of existence for an arbitrary bounded solution, you're converging weakly to a compact solution. So these compact solutions are the bubbles in this equation that you extract. And this happens for any bounded solution. So if you want to understand the asymptotics of bounded solutions, because of this theorem, you need to understand compact solutions. Now, this theorem is valid in generality. It's not just for the nonlinear wave equation. It's also true for the nonlinear Schrödinger equation, for KdV, and for many other dispersive equations. Okay, and that's also proved in the same paper. Okay. So the next thing I want to tell you is, what do we know about compact solutions? The first thing you would ask is, what are the radial compact solutions? Right, that would be your first question. And so here we have U compact, U radial, then U has to be W. There's nothing else. This explicit solution that I erased of the elliptic equation. Okay? So the next thing so at least one of T minus and T plus must be infinite. So for compact solutions, if you blow up in only one time direction. Of course, if they are all traveling waves given by Lorentz transformation of an elliptic solution, they never blow up. But this gives you halfway there. Then in a paper with Burrell in '08, we showed that if U has compactness property, let's abbreviate, U compact, T plus is finite, then there's a concentration in the light cone for this. So what that means is that the supremum, I mean not the supremum, the support for T in the interval of existence of U of T dt of T is contained picture is this is x plus, this is time t plus, we have the backward cone, and this is where the solution has to live. And that's a consequence of the finite speed of propagation and the compactness. Okay? So if you have a finite time of blow up, the solution is concentrating extremely well. And the scaling parameter is going at a linear rate from below. Okay, and so this is the speed given by the light cone again. And that's a bound from below. But the next thing is that if this is the exact rate, then U cannot exist. So you cannot have any compact solution that blows up in finite time at the speed of the light. Okay? So the proof of this, I'll comment on this a little bit later. And then the next result that I want to mention two more results. This is all we will know. U compact. There are two sequences of time converging to the final times, which could be infinite, and two elements, Q plus and Q minus. In sigma, sigma, I recall, are the non-zero solutions to the elliptic equation. And a vector L of length less than 1, so it's a candidate for a Lorentz transformation, such that up to modulation, that means up to translations and scalings, then U of Tn plus and minus dt of U Tn plus and minus converge strongly to Q plus minus L at time 0 and ddt of Q L plus minus at 0. So what this means is that the conjecture that all compact objects are Lorentz transformations of elliptic solutions is true asymptotically. So asymptotically, as you converge to the final time, you can find a QL, one at the positive time and one at the negative time. Okay. So the conjecture is that 0 and QL are the only compact solutions. And the last result, if Q plus or Q minus is non-degenerate, then U is actually equal to the QL plus to the QL minus. Now, the non-degenerate condition is a little bit of a technical condition having to do with the spectral properties of the linearized operator around Q plus and Q minus. But it's a standard kind of assumption in when doing spectral analysis or in geometric problems. Okay. So this is the state of the art here, and this is the explanation of why you want to do it. And what I'm going to explain in the rest of the talk is a little bit of an advance, which we know that one of t plus or t minus has to be finite. Now we can prove that both of them have to be finite. So this is the theorem for today. Okay? So the theorem they're both infinite. That is to say, any compact solution exists globally in both time directions. So the rest of the proof is going to be spent in giving some ideas for the proof of this result. Okay. And of course, this is evidence about the validity of the conjecture that all compact solutions are Lorentz transformations of elliptic solutions. Now, I started by discussing the Soliton resolution conjecture, and you could very validly ask me, in order to prove the Soliton resolution conjecture, do you need to solve this conjecture about compact solutions? Right? You could ask that, and it would seem that the answer should be yes. But things are more complicated. It is not quite necessary to do that, and the reason for that is that the Soliton resolution conjecture is an asymptotic conjecture. And therefore, all you should need is asymptotic information. And we already have the asymptotic information here. But nevertheless, this is an interesting problem. And the hope is that it reveals part of the behavior of solutions. Okay? Okay, so first I'm going to give you some idea of how one proved this result, in order to go to the proof of that. Because the proof of that is an extension of this. Okay? And there's an interesting circle of ideas here, because what it does is it uncovers a parabolic aspect of the nonlinear wave equation. So at a certain scale, the nonlinear wave equation has some kind of parabolic behavior. And this is a very important fact. So, So in here, by translation, assume that x plus is 0, which you can clearly do. X plus is the point at the tip of this cone, and we can make it to be 0. Okay? And we can also make t plus to be 1 by scaling. Okay? So the idea is to now introduce self-similar variables. So I'll write that down. So we introduce So we rewrite the nonlinear wave equation in self-similar variables. Now, this idea comes from the study of singularity formation to parabolic equations. This appears first in the work of Giga and Kohn on the singularity formation for nonlinear parabolic equations. And so you just do this, and now we write down the equation for W. And I'm going to write it here. And I'll tell you what rho is in a minute. And again, I'm doing this for n equals 3. The numbers are different otherwise. Okay, so this becomes, so this part seems a little bit like a wave equation. Of course, we have 2 time derivatives here, 1 space derivative here. But there's a twist in that the wave equation is degenerate because we're introducing this weight, which degenerates at y equals 1. And the second thing that we have is this transport terms here. And what happens for this equation is that the energy is time increasing. So this is kind of a backward parabolic effect. And you compute that energy, see that it's time increasing, and that gives you some sort of Lyapunov functional with which to study the solutions, and you end up by proving that if you have a solution to that had inherits the compactness property, then it has to be 0. And that boils down to a unique continuation theorem in elliptic equations. So there's an elliptic element of that proof. Okay, and that's how that proof over there went. Okay. So now let me give you the idea for the proof of this theorem. First is a proposition 1. Says that U, a bounded solution of NLW, let's say that its finite time is 1, and its backward finite time is minus infinity. So it exists in the negative direction for all time and blows up at t equals 1. Okay? And we are going to assume the support property. which corresponds to this. Okay? Then there's the following estimate. As t goes to minus infinity, we get the following obvious estimate. And I mean obvious in a sarcastic way. This limit of averages of the L6 norm as time goes to negative infinity is strictly smaller than the energy of U. Okay, so how do you prove such a thing? The way to prove that is to use the self-similar variables here. Okay? So that's the first ingredient. Now there's two more ingredients. So there are two cases. Let's call case A. So we're trying to prove the theorem over there. In case A, we assume that the lambda, as we go to minus infinity, remains linear, of linear size. Okay? That's the first possibility. Then you prove that no such U can exist. Then no compact U other than 0. Now you would think that that reduces to this theorem. And that's what we thought for a long time, and we never could do it. But then we decided to change strategy, and instead of reducing it to the previous theorem, try to mimic the proof. And then that worked. Okay. So it's not a direct reduction, but it's the same style of proof, using, again, self-similar variables. So this case is taken care of because it can't be. In case B, is that this thing then tends to 0. I have to say this inequality here is always true by finite speed of propagation. And it's the analog of this inequality here. Okay. So this is the case we need to deal with. So in this case, we use virial identities. So these are some formulas that govern the behavior of these equations. But you can only use them under this assumption. And they are the following. So these things are just some clever integration by parts, and where you exploit the fact that the lambda of t over t goes to 0 by introducing suitable cutoff functions. Okay? And this in the trade are called virial identities, the formulas that you use. You may have seen them under the form Morowitz identities or other multipliers, but they're all of the same style. Okay? Now recall that the energy you see here, these numbers are all crucial. This is constant in time. Right? So, and remember also this fact. 1/2 minus 1/6 is 1/3. Then you use these things and you conclude that this limit is the energy. Because if you integrate the energy here, if you take the average of a constant, you get the constant, and you just add and use that 1/3 is 1/2 minus 1/6. Okay? But now you look at this thing, and you look at this thing, and you're beginning to see a contradiction. And the contradiction is given by a Tauberian lemma. So I write down the Tauberian lemma. So this Tauberian lemma is a calculus lemma, of course. Suppose that G is continuous and bounded. Suppose that the limit as t tends to infinity of 1 over t integral from 0 to t of g of t dt is some number L, which is finite. Then the limit as t tends to infinity of 1 over log of 2 plus t integral between 0 and t of g of t divided by 2 plus t dt is also L. So that would be a Tauberian type theorem. Right? You have one average, and you look at the different average, and the limits are the same. Now we just apply this is the assumption here. Right? And so when we do the logarithm and so on, we should get the energy. But our proposition said that this limit, which is exactly what you need to have here when you reverse time, is strictly smaller than the energy. So that's a contradiction that comes from assuming that t plus was finite. So such a thing cannot happen. So these are global properties, so you have to work with global quantities. There's no size restrictions, everything is large. So the moral is that when you're doing nonlinear analysis in the large, the only thing you have going for you is monotonicity formulas that you have to discover. And these are all the monotonicity formulas we have. And so that's how the theorem goes. That's it. Thank you.